something arrived from the void. Not light, not radio waves, not the gentle whisper of distant starlight. Something ancient, something impossibly energetic, a single particle, screaming across the cosmos with the force of a thrown baseball. It crossed the abyss between galaxies, and it came from nowhere. Nowhere at all. Imagine it. A quiet November evening in the year 2021. High in the mountains of Japan's Osaka Prefecture, the Osaka Metropolitan University Cosmic Ray Observatory spreads across the landscape a vast network of 527 detectors, scattered across an area of more than 700 square kilometers. The instruments work in silence, capturing invisible traces of cosmic visitors. And then, impact. Something arrived from the edge of the universe, and the detectors trembled. Scientists stared at their screens. They read the numbers again and again, unable to believe what they were seeing. It was her, the Amaterasu particle, named after the Japanese goddess of the sun, ruler of light and the heavens. This particle became one of the most enigmatic discoveries in the history of modern astrophysics. But before we plunge into the abyss of this mystery, let us take a step back. Because to understand why scientists were shaken to their very core, we must first understand what cosmic rays are, and why a single proton can overturn everything we thought we knew about the universe. Every second, on every square centimeter of Earth's upper atmosphere, a genuine storm of invisible particles from the depths of space rains down upon us. Protons, helium nuclei, nuclei of heavy elements. They fly toward us from every direction, ceaselessly, unstoppably, for billions of years. Most of them are born relatively nearby within our galaxy, in the remnants of supernova explosions, in the powerful magnetic fields of neutron stars and pulsars. These particles carry enormous energy by the standards of ordinary physics, but even they are merely a whisper compared to what sometimes arrives from much farther away. There exists a special class of cosmic rays, the ultra-high energy variety. Their energy is so colossal that each such event is a true rarity. One such ray strikes an area the size of a football field once per century, once, in 100 years. And that is precisely why detectors spanning hundreds of square kilometers are the only way to catch them. The first such monster was the famous Oh My God particle of 1961, detected in the American state of Utah. Its energy was approximately 300 exelectron volts, a number that means almost nothing to an ordinary person, but makes physicists go pale. Imagine a single subatomic particle smaller than a proton, invisible to the naked eye, carries within itself energy comparable to a thrown tennis ball. Not an atomic bomb explosion, not a meteorite impact. One tennis ball. It sounds almost laughable until you remember that we are talking about a particle 1 quadrillion times smaller than an atom. Amaterasu surpassed the Oh My God particle by roughly a factor of 2. Its energy was estimated at around 240 exelectron volts, placing it among the most extreme events ever recorded. But it was not just the energy. It was where the particle came from. When a particle carries such a monstrous reserve of energy, something important happens. The galaxy's magnetic fields are virtually powerless to alter its trajectory. Ordinary cosmic rays, traveling toward us for millions of years, are twisted and bent by the magnetic fields of interstellar space, and by the time they arrive at Earth, their original direction has been completely lost. They arrive as if from random points in the sky. But ultra-high energy particles are different. They fly in almost a straight line. They are arrows, fired from a specific point by a specific archer. That is precisely why scientists were able to trace the trajectory of Amaterasu backward toward its presumed source. And this is where things become truly frightening. The trajectory pointed toward what is known as the local void. This is not a metaphor, and not a poetic exaggeration. It is a real region of space, a vast, nearly empty zone of the universe, located tens of millions of light years from our galaxy. Within it, there are no powerful radio galaxies, no active galactic nuclei, no clusters of galaxies with their titanic black holes. There is nothing, absolutely nothing, that by our current understanding of physics would be capable of accelerating a particle to such a boundless energy. Stop for a moment. Breathe. The particle came from the void, from a place where nothing exists, and it carries within it energy that nothing was there to give it. This is not merely a puzzle. This is a challenge to all of our physics, all of our cosmology, everything we believed we understood about the universe. Of course, scientists did not give up. The first and most cautious hypothesis is measurement error. Perhaps the trajectory was determined imprecisely. Perhaps the source is, after all, slightly off to the side in a region where galaxies capable of producing such a particle actually exist. This is an honest and legitimate question. Astrophysicists examined it carefully. The angular uncertainty in the arrival direction of Amaterasu amounts to several degrees. Even shifting within this margin of error, we still land in a region extremely sparse in known powerful sources. Not a single suitable galaxy was found nearby. The second hypothesis concerns intergalactic magnetic fields. Despite the particle's enormous energy, intergalactic space is not perfectly empty. Within it exists the weakest of magnetic fields, literally millions of times weaker than Earth's own. But across a distance of tens of millions of light years, even such a feeble field could theoretically nudge a trajectory by a small degree. If so, the true source might lie slightly off the indicated direction, in a more cosmically populated neighborhood. This hypothesis is appealing in its simplicity, but it has a problem. To deflect a particle of such energy by any meaningful angle would require fields far stronger than anything we have been able to measure in the intergalactic medium. The third hypothesis already ventures to the boundary of science fiction, but crucially, it does not contradict modern theoretical physics. Topological defects in spacetime. From the very moment of the universe's birth, in the first instance after the Big Bang, when the fabric of reality was still a roiling, incandescent plasma, certain structures may have formed within it cosmic strings, magnetic monopoles, textures. These are not metaphors. They are specific mathematical objects predicted by several models of the early universe. Cosmic strings are one-dimensional defects, threads of space-time of monstrous density, left behind like scars on the body of the universe. When such structures interact or decay, colossal reserves of energy could be released in the form of ultra-energetic particles. If somewhere in the local void such a process took place, it would explain everything. But it would also mean that we have, for the first time in history, detected a particle, a messenger from events that unfolded in the very epoch of the universe's birth. The fourth hypothesis is the darkest and most breathtaking of all: dark matter. We know it exists because we see its gravitational influence on galaxies, on galaxy clusters, on the entire large-scale structure of the cosmos, but we do not know what it is. One theoretical model proposes that dark matter consists of so-called super-heavy particles, relics of the early universe, whose mass exceeds that of a proton by quadrillions of times. If such a particle decayed somewhere in the void, it could have given birth to exactly this kind of ultra-energetic cosmic ray. And then Amaterasu would not be merely an anomaly. It would be the first direct observation of a process tied to the very nature of dark matter. But there is something else, something that scientists discuss in whispers, and that popular publications address with simultaneous wonder and caution. What if the source of this particle was not a natural process? Wait. Stop. Don't be too quick to smile. This is not cheap sensationalism. This is the logical consequence of serious science. Back in 1964, Soviet astrophysicist Nikolai Kardashev proposed a scale of civilizations based on their capacity to harness energy. A Type 1 civilization uses all the energy of its planet, Type 2 all the energy of its star, Type 3 all the energy of its entire galaxy. On this scale, we, the people of Earth, have not yet reached even the first tier, but a Type 3 civilization. That would be beings or systems capable of operating with energies that are, for us, literally unimaginable. The weapons of such a civilization, the engines of such a civilization, the signals of such a civilization. All of these could theoretically produce exactly such particles anomalous, impossible, flying out of the void. Of course, this is the most extreme of all hypotheses, and it has no evidentiary basis whatsoever. Scientists do not write this way in official papers. But in private conversations, at conferences, in hallway discussions, the question surfaces. Because the universe is old enough for civilizations to have arisen within it that are billions of years older than ours. And we do not yet know where they went. Amaterasu is not the only such anomaly. It stands alongside other ultra-high energy events, the Oh My God particle of 1961, the so-called Fly's Eye event of the 1990s, and dozens of other detections by the Pierre Auger Observatory in Argentina. As our detectors grow more sensitive and their coverage area expands, we detect more of them. And every time the same question: from where? What produced them? What is moving through the fabric of space, leaving such traces behind? The detector network continues its work. Japanese and American scientists analyze the data, search for correlations, build maps of the sky trying to determine whether these ultra-energetic visitors arrive preferentially from certain directions. If several particles arrive from the same region of the local void, that would no longer be coincidence. That would be an indication of a source, of something specific, of something real. But for now, silence. For now, we stand before this mystery as a person might stand on the shore of an endless night ocean, staring at a solitary light in the distance. Where did it come from? What is there? Who lit it? The universe is vast. It is older than anything we are capable of imagining. It is 13,800,000,000 years old. It has survived epochs we can describe only in mathematical formulae, the first instance after its birth, when everything was light and heat, the cosmic dark ages, when not a single star existed, the era of the first galaxies rising from primordial chaos. In all that time, anything could have happened within it, and the traces of it are still flying toward us through space. Amaterasu is a reminder that we know extraordinarily little, that the map of our understanding of the universe is full of blank spaces, and it is precisely in those blank spaces that the greatest discoveries lie hidden. A reminder that science is not a collection of ready-made answers, but an eternal, gripping, endless pursuit of questions. And every such particle, every solitary messenger from the depths of space, is a new question, thrown at us by the universe itself. We will answer. Sooner or later, we will answer. Because that is precisely what makes us human. If this video made you stop and think, leave a like. Write in the comments, which hypothesis seems most convincing to you? A topological defect, dark matter, or something else entirely? Something we have not yet begun to suspect? Subscribe to the channel so you don't miss the next journey into the depths of the universe. Stay with us, and until we meet again.